This is an incandescent light bulb. Its light comes from electric current passing through a thin piece of metal. Although it looks white, refracting this light shows that it actually consists of all colors of the rainbow. This is what's known as a continuous emission spectrum.
Then, there's this mercury vapor lamp. It doesn't have a solid filament. Instead, it produces light by electrifying gas. At first glance, its light looks a lot like the incandescent bulb from before, but its refracted spectrum tells a different story. Instead of a continuous rainbow, we see a discrete set of separate colors. This is called a line spectrum.
Then there is the sun. Like the incandescent bulb, it emits a white light that refracts into a continuous spectrum. But we're told by astronomers that the sun is a burning ball of gas and plasma. What gives?
One possibility, and the one that's favored by modern solar scientists, is that high-energy photons released by fusion reactions deep in the heart of the sun bounce around for millions of years on their way to the surface. By the time the light escapes to Earth, it's cooled into photons of all the right colors to make up a continuous spectrum.
But there is another possible explanation. The sun has the continuous spectrum of a condensed material because that is a better description for what it is. This isn't exactly a new theory. Condensed matter models of the sun have been around since the mid-1700s, but its modern reemergence is ruffling some feathers. That's because if the sun isn't actually a gas, if there was a mistake made nearly a century ago, then there's a whole lot of astrophysics and cosmology that's gonna have to be reimagined.
So, what's the argument for a liquid metal sun, and what does it mean for the central theory of cosmology, the Big Bang? Well, it's a story of paradigm shifts, pop science princes, and a fair dose of old-fashioned politics. Believe what you will, but here's the saga of the scientific understanding of the sun, from liquid to gas, and maybe right back again.
Theories like those of John Herschel suggested that the photosphere, the glowing surface of the sun, was a layer of luminous clouds underneath which there was a solid surface that hosted a Solarian civilization. Scientists abandoned Herschel's version of an inhabited sun with the help of Gustav Kirchhoff and his invention that would establish the modern discipline of astronomy, the spectroscope.
The instrument's eyepiece was a portal into the secret life of substances. With his eye pressed against it, Kirchhoff was able to watch how substances behaved in the heat of a flame. To an observer in the room, they gave off bright colors, but refraction through the spectroscope's internal prism told a more complex story. Hot, excited gases gave off the characteristic line spectra we saw at the beginning of the episode. He soon realized that these unique barcodes could be used to identify the compounds in an unknown sample. He also found that liquids and solids produced continuous spectra and discovered that gases, when placed between a hot object and the prism of his spectroscope, cast dark absorption bands upon the heated body's continuous spectrum. These dark bands correspond exactly to the line spectra of the gas's own emissions.
Kirchhoff quickly realized that his instrument gave him the ability to study the sun to a level of detail that had never before been achieved. He built a spectroscope that gave him the ability to project the solar spectrum directly above one generated by his flame in the laboratory. By comparing the bright lines cast by the flame with the dark lines of the solar spectrum, he was able to derive the composition of the solar atmosphere. At the end of this project, he published his work and stated that the sun, quote, consists of a solid or liquid nucleus heated to a temperature of the brightest whiteness, surrounded by an atmosphere of a somewhat lower temperature.
It was a robust theory based on many years of observational data, but Kirchhoff was working within an increasingly math-centered academic culture, and his researches on the solar spectrum and the spectra of the chemical elements didn't contain a single equation, so it was no surprise that the scientific community preferred a more quantitative story of the gaseous sun, told by way of the then recently popularized ideal gas law. Despite the qualitative nature of Kirchhoff's theory, it's possible that it could have eventually gotten the mathematical treatment necessary for widespread success. That is, if it wasn't for the influence of one Arthur Eddington, the Neil deGrasse Tyson of his day.
There is no way to describe Arthur Eddington except as the it boy of early 20th century science. He rose from humble beginnings, a fatherless Quaker child raised by a single mother on the English seaside to become a graduate student of natural sciences at Trinity College, Cambridge. When he arrives there, it first seems that science is about to get away from him. He starts a project in physics and quickly abandons it, then a project in mathematics, and he abandons that too. Just as he is about to resign himself to a career as a math tutor, one of his seniors at Trinity secures him a position at the Royal Observatory.
There, Eddington blossoms. He finished his outstanding projects, publishes papers, develops new statistical methods, shakes hands, takes names, and even gets appointed chair of experimental astronomy at Cambridge. A year later, the theoretical chair dies, and Eddington becomes the director of the entire observatory. He is 31 years old. Awards rain down on him. He's named a Fellow of the Royal Society, gets gold medals from both the Royal Society and the Royal Astronomical Society, of which he serves as president shortly afterwards. He is asked to give the prestigious Beckerian lecture, and somewhere in there, gets knighted.
Along the path to academic canonization, he comes across a few papers by a young German physicist named Albert Einstein. Sensing that Einstein has something unusual to say, he becomes a student of relativity. He lectures on it at the Royal Society, translates Einstein's work into English, and even takes on the burden of finding experimental proof of bent spacetime. He ships an astrographic lens to Principe Island off the coast of Equatorial Guinea and vows that he will prove Einstein's theory of general relativity once and for all.
The voyage is hailed as an enormous success for relativity. Not because the experimental measurements they took were very good. They weren't. The eclipse was obscured by clouds on 15 of 16 photographic plates. It was a success because Eddington declared it so, after he measured Einstein's prediction on a single blurred plate. In the wake of the expedition, Einstein himself anoints Eddington, telling the press that his book, The Mathematical Theory of Relativity, is, quote, the finest presentation of the subject in any language. With his reputation secured, Eddington is free to move on to other topics, like the sun.
His reputation was further cemented when he theorized that suns fuse hydrogen as their source of solar energy, resolving a lingering question about what prevents stars from collapsing under their own gravity. He also formulated the mass-luminosity equation, which extrapolated the mass and brightness of the sun to stars in general. Both of his models were very popular, and for good reason. Fusion answered the question of heavy element provenance, and mass luminosity was a simple observation. Stars with more gravity generally seem brighter. The coup for the theory of the gaseous sun was that the quantitative details of both constructions assumed the ideal gas law. Whether or not a gaseous sun fit with what was observed spectrally and structurally didn't really come up.
Of course, there were criticisms of Eddington's work. In the most mean girl thing imaginable, Einstein once wrote in a private letter that, quote, Eddington was, as a rule, uncritical towards his own ideas. This is echoed by the physicist and mathematician James Jeans, who insisted that, quote, all Eddington's theoretical investigations have been based on assumptions which are outside the laws of physics. But Jeans didn't have the charisma or reputation necessary to undo the impact of Eddington's work. No one did.
Today, most astronomers stand behind the gaseous sun. After all, if the sun is a gas or a gaseous plasma, then the ideal gas law is enormously valuable for deriving fundamental characteristics of our nearest celestial neighbor. But remember, with enough mathematical maneuvering, early astronomers were able to prove that the Earth was at the center of the solar system. The complex epicycle mathematics that justified that assertion were only brought under appropriate suspicion when a simpler model became impossible to ignore.
At some point in the last 100 years, physicists began to believe it was possible to calculate their way to understanding the natural world. Eddington himself boasted that if he never once saw the sun, he would still have been able to derive everything about it. The rising popularity of relativistic mathematics further poisoned the well, centering the role of observers in nature. Eventually, elegant mathematical constructions came to replace the study of material interactions at both the atomic and cosmic scales. Reversing this tide has been a slow and thankless process, largely because mathemagic is so esoteric and so successful in technological applications. Inquiring as to the physical interpretations of the mathematics is considered utterly naive. Who would go on record to contradict Eddington or Einstein?
Almost no one, for the immune system of the scientific establishment is a fearsome obstacle, which is why the resurrection of the liquid sun has largely fallen on the shoulders of one man, Dr. Pierre-Marie Robitaille. His argument rests on the foundational principles of radioimaging, with which he became familiar during his time at Ohio State University, where he designed the world's first ultra-high field MRI scan. You can listen to our conversations on demystifying science. What he realized was that astrophysicists were treating the sun as a gas but applying spectroscopic laws derived for use with solids and liquids. For example, consider the temperature of the sun, which appears to violate the second law of thermodynamics. The internal temperature of the sun, arrived at through the ideal gas law, is currently thought to be 15 million Kelvin. The corona, the outermost part of the sun, is thought to be at least 1 million Kelvin. So far, so good.
But sandwiched between these two layers lies the photosphere, which spectroscopically appears to be only 5,700 Kelvin. Robitaille's explanation is that scientists arrived at this number from a combination of Wien's, Kirchhoff's, and Planck's laws, which together relate the peak emission frequency of a radiating body with its temperature. However, these laws were never intended to be applied to gases since, as Kirchhoff discovered, they do not give the necessary continuous spectra. The reason that a pure sample of an excited gas gives off discrete wavelengths of light has to do with the way its electron shells vibrate when they're excited. Much like the fundamental frequency of a plucked string depends on its length, the gaseous atom's vibration has to do with its geometry. Since each atom has a distinct shape, it gives off a correspondingly unique set of light tones.
Solid or liquid material, on the other hand, exhibits a lattice that is articulated at countless points. Vibration is no longer limited to fundamental atomic frequencies. Instead, vibrational overtones appear throughout the entire lattice, which produces a continuous spectrum. Perhaps if Dr. Robitaille's conclusions about the nature of the sun ended at a reimagination of its temperature, his work would be more widely accepted. The problem is, he believes that the mistake is not limited to solar physics. In his view, misapplication of these laws invalidates the claim that the cosmic microwave background radiation, the CMB, is a 13.7 billion-year-old echo of the Big Bang.
The conventional explanation of both the sun's and the Big Bang's perfect thermal spectrum are very similar. High-energy photons, produced by fusion in the sun and by the first gaseous hydrogens in the Big Bang, undergo a series of complicated transformative relay events until they can recapitulate a perfect Planckian spectrum. However, Dr. Robitaille is quick to point out, gases can't give these kinds of continuous spectra. So, what is his replacement for the conventional theories?
In the case of the sun, Dr. Robitaille suggests it would be wiser to consider it to be made of liquid metallic hydrogen. This would give the sun the hexagonal lattice that's necessary to emit a perfect thermal spectrum, while remaining true to the compositional necessities for a fusing stellar body. In the case of the CMB, its microwave signal is that of a perfect black body with an apparent temperature of 2.7 Kelvin. If we accept that gases cannot give a continuous black body spectrum, then we have to ask, where is the signal coming from?
Dr. Robitaille suggests it is the ocean itself. The signal is at 2.7 Kelvin instead of ambient ocean temperature because it isn't coming from the well-characterized angle-dependent intramolecular OH bond. That polarized radiation is absent in the antenna at sea level, as shown in this graph of apparent temperature versus measurement angle. Instead, the radiation that spilled into Penzias and Wilson's antenna came from the intermolecular hydrogen-bonded lattice of the ocean's water, which acts as an apparent black body, which only gives an apparent temperature. In support of this theory, Dr. Robitaille points to Harouni's antenna, a radio telescope built high in the mountains of Armenia, angled in such a way that prevents contamination from spillover radiation. There was no CMB detected at Harouni's antenna, and in the decades since, it's fallen into disrepair. But efforts are underway to raise funds for refurbishment and continued experiments, so we'll keep an eye on it and fill you in on any developments.
So does this strike a death knell for the Big Bang theory and the gaseous sun? Well, probably not in today's socio-political milieu. Dr. Robitaille does not have the preeminence of Eddington or Sagan or Neil deGrasse Tyson, but he is the father of ultra-high-field MRI and has published dozens of papers in Progress in Physics, a journal that promotes academic freedom. He also has more than 100 videos on the Sky Scholar YouTube channel explaining why the sun cannot be considered a gas, and why the CMB does not tell us anything about the Big Bang or the temperature of the universe. We've listed them in the description for anyone who wants to know more. The reality is that science is about stories, and the stories we tell have to be compelling. A gaseous sun enables other stories people hold dear. Science is infallible, humans understand the solar system with extraordinary precision, and just like human life, there was a similar birth of the universe, and there will be a corresponding death.
The pain of paradigm shifts is real. And that pain is carried by the brave men and women who are willing to become pariahs, speaking their vision of science to a world that isn't ready for them. But the beautiful thing about science is that eventually it will move forward. It may take a long time, and there may still be more Eddingtons to come, but there's whispers of an entire realm still waiting to be explained. Hey, what's up, humans? I'm Michael Shiloh.
I am Nastya.
We are Demystifying Science. If you enjoyed what we did today, please check out our Patreon page at DemystifySci.
It would be life-changing for us if you became a patron and pledged whatever amount you can afford per month. We love doing these videos, and that is how you can make sure that we can keep doing that.
So come find us. We'll see you at DemystifySci on Patreon. And we'll be back with more videos soon.